I am Omar, and I work for ETA, one of the partner of the B-WaterSmart project. This is the agenda for today. We will talk about the extraction of nitrogen from centrates and recovery of ammonium sulfate as fertilizer. The Venice case is a part of the project, of the B-WaterSmart project, and there are 6 members. 2 are multi-utility companies, and 2 are that are Veritas and Netra. 2 are private companies in the sector of recovery of water and wastewater treatment plants and so on, that are Hydrotech and Depuracque. Then there is Sintef, that is our mentor, and engineering, that is an IT company. Our living lab focuses mainly on water recovery, management of sludge, and nitrogen recovery from the streams that are managed inside the wastewater treatment plants, and its recovery as fertilizer. The 2 main partners in the pilot tests of the technologies to recover the nitrogen are ETRA and Depuracque. Well, our focus is on the recovery as fertilizer. Usually, in ordinary process in wastewater treatment plants, we manage 3 fertilizing elements that are phosphorus, that are segregated inside the biomass of the sludge, carbon, that is decomposed to CO2 and released in the atmosphere, and mainly it is part of the biomass of the sludge, 35% on dry matter, more or less. And the last one is the nitrogen, our element of study, that is mainly transformed in molecular nitrogen, and it, in this form, passes to the atmosphere, and a little part, some milligrams per liter, exit the plant with effluent, and more or less the 5% of the sludge is composed by nitrogen that forms, of course, a part of the biomass. Which are the number? What are the number we have to deal with talking about nitrogen as recovered fertilizer? These numbers are an estimation for our entire region, Veneto. As you can see, about 5,000 tons per year of nitrogen is inside the effluent, remain inside the effluent, and could be recovered with irrigation. Other 2,000 tons per year are inside the sludge that are suitable for the agricultural reuse, and they are almost entirely recovered. And there is another smaller part, 600 tons per year, that could derive from centrates. Centrate is the liquid fraction of the watering of the digestate, deriving from the anaerobic digestion of sludge. On the right side, you can see some percentage. These percentage are the percentage of the total mineral nitrogen fertilization of the region. And as you can see, each fraction of the total nitrogen that can be recovered is small, because the fertilization in Veneto is nitrogen fertilization is very diffused and very used, and approximately 70,000 tons per year of nitrogen is used as mineral fertilizer. But these are small numbers, what we can recover. But we think that it's worth to understand better the issue, because about the nitrogen fertilization, we have some problems, because EU totally depends from non-EU countries, but for the to have the fertilizer and to have the raw materials. It means that we are hostage of the variation of prices that we saw, particularly during the pandemic and after the war, the Ukrainian war. And another problem is that mainly the nitrogen fertilizer is produced by Haber-Bosch process that works at very high temperature and pressures, and it is the highest energy and emission intensity among major industries in the world. So the impact, the environmental impact, is very high, especially in terms of GHG emissions. This table shows the main technologies that can be used to recover ammonia from wastewater. Well, I think that in our sector, we use using centrate, we have very dirty water, and I think that membranes and ion exchange can't work very well. Chemical precipitation means the production of struvite that for stoichiometric problems is usually used for the production, for the recovery of phosphorus much more than nitrogen. Stripping is the last technology, and is the technology we have used in our test. The general principle of stripping is that inside wastewater, ammonia is present in two species: ammonium as salt and iron, and ammonia. Ammonia is a gas dissolved inside the water, and if you let an airstream cross the wastewater, the gas ammonia follows the airstream, and this stream enriched in ammonia can be put in contact with an acid, for example, sulfuric acid, to produce a solution of a salt, ammonium sulfate in this case. And in this way, you can recover the ammonia present in the wastewater. The two main parameters that influence the yields of this process are pH and temperature, as you can see in this figure. And the higher are both pH and temperature, the higher is the yield. Well, after this short introduction, I give the floor to Davide and Paolo, that we talk about the two technologies we have used during the pilot test, that are column stripping and aeration stripping. I leave the chair to Davide that will talk about column stripping.
Thank you very much, Omar. Hello, everyone. My name is Davide Carraro. I work with the Buracque Servizi, which is a huge environment in the Venice area. We engineer a wastewater treatment plant, and today I'm going to show you the principle that stands beside the column stripping technology. So I would like to start with a theoretical background. As you can see from this slide, every column stripping plant is based upon two columns. The first one on the left is called stripping column, whereas the other one on the right is called absorption column. Let's start from the stripping column. As you can see, every ammonia-rich wastewater enters inside the first column, and then through some nozzles it is sprayed downfalls, and by gravity but reaches the bottom of the column. Meanwhile, there is a countercurrent air flux which is in contact with the liquid phase, and by heating up the stream to high temperature and increasing the pH to basic values, we are able to increase the ammonia phase transfer from the liquid phase to the gaseous phase. The column is packed with random packing, which promotes furthermore this phase transfer. So overall, at the bottom of the column, we are able to obtain ammonia-free wastewater, which is discharged or passes through another treatment. And the gaseous phase, which is rich in ammonia, enters inside the second column, in which there is a recirculation of an acid. In this case, I put sulfuric acid, and the outcome is the product of the reaction between ammonia and sulfuric acid, which is ammonium sulfate, which can be discharged after a proper concentration step. And the clean air which remains after this process can be recirculated inside the first column. So we are able to obtain a closed circuit. The main factor which affects the concentration of ammonium sulfate is the pH. I mean, after we reach a specific pH value, we are able to discharge the ammonium sulfate solution. However, due to the fact that ammonia phase transfer has to keep efficient inside the packed bed column, we must avoid any formation of solid inside the stripping column. And as I said before, since we proceed by alkalization, which can be performed by dosing either lime or soda at a pH value above 9, and in order to move the equilibrium towards ammonia phase transfer through gas phase, we have also to heat up our system at a temperature above 50 degrees Celsius. It happens that for every wastewater which enters the column, that in case of presence of any suspended solid or also other substances that through pH or temperature increase can precipitate inside our columns and interfere with the phase transfer, we must remove all of these species before the wastewater enters the column, and therefore we need to put a pre-treatment section in order to remove both total suspended solid and alkalinity, since any hydrogen carbonate ion in presence of calcium ion can cause the formation of limestone, which precipitate and interfere with phase transfer. Therefore, we designed a batch pretreatment reactor in which the wastewater input is added with proper alkalization agents. This treatment causes the formation of some sludge, which are removed from the reaction, and the treated water is allowed by a further filtration step to enter our plant. Overall, so in this slide I show how our stripping plant worked. As you can see from this image, from the right to the left, we have the wastewater hold-up tank, the flocculation sedimentation reactor in which is performed the alkalization pretreatment, and the wastewater reaches the two columns. Here on the right, you can see the first one, absorption column, which is made up of stainless steel. In this case, the stripping column, sorry. Oops. And on the right, the absorption column, which is made of a plastic material, since it has to be in touch with the concentrated sulfuric acid. In conclusion, our plant is able to allow a continuous flow process, beside the fact that the pretreatment reactor is dimensioned with proper dimensions, which are able to guarantee a continuous feeding to the column. Our system, with respect to other technologies, is more compact and small size, but above all, it can guarantee high to quantitative ammonia removal efficiencies. Since we are able to control either pH or temperature, our working conditions are very flexible, since we can modulate both working pH and temperature, as we can see later in the results section. And as I said before, the fact that we recirculate the gaseous stream allows us to avoid any atmospheric emissions. However, there are also some disadvantages. I have to mention that our pretreatment, of course, generates sludge, which has to be properly disposed or destroyed. We unfortunately have to precondition the wastewater input in order to remove both suspended solid and alkalinity. And in order to our condition to be representative, we must run our experiments to a minimum flow rate, which stems from 2015 to 500 liters per hour. So I have concluded my section, and now I leave the chair to my colleague Paolo, who is going to present another stripping technology. Thank you very much for your attention.
Good morning, everybody. I'm Paolo, I'm collaborator of ETRA. ETRA has tested a different kind of technology that is called the air stripping technology, that is based on the same principle of the technology presented before from my colleague, but there are some differences. But first, I want to say that, okay, we were the tested partner of this technology, but was provided from a local private company that built up a project, the testing pilot. The air stripping technology is based, as I said, to the same principle. So we have a stripper and a sober part. But the main difference is that we feed the stripper directly with the solution that we are going to treat. So we don't have, in this case, a pre-treatment, as I said before, but we move inside of the stripper, that is a tank, where we are going to heat the solution, thanks waste heat or other source of heat, or in this case for us it was electricity, just because we use a pilot scale plant. And inside the stripper we have the air injection from the bottom with nozzles that create small bubbles that are passing through the concentrate or through the waste water that we are going to treat. And thanks to the heat, we create ammonia that we are taking out, and we are going to move to the absorber. Here is like before, there are some columns that explained before from my colleague, where we have the air that is entering from the bottom part and is going to counterflow with sulfuric acid that are going to produce ammonia sulfate that is going to be on the bottom. The air that already was passed through the absorber, that is without ammonia anymore, is going to go back to the stripper. But in this case, we are not able to create a closed circuit of air, not for all of it, because we have to take out a percentage, a part of the circulation air through a purge. It's because inside the stripper we have a reaction with carbonates that are going to produce CO2 and other degradation like organic volatiles or something else that we have to take out to don't avoid the reaction inside the stripper. And so a percentage of air has to be sent out, and at the same time, so the same amount has to take from outside with as a fresh air. And this will change according with the percentage of purge, the some efficiency that after my colleagues are going to present to you. But is a specific effect of this technology that needs fresh air, and a part of it has to discharge. Inside the stripper, we can work maybe changing the pH if we want, using soda or other solution or chemicals to manage the process inside the stripper. In the same times, we have some troubles that are to solve in a real scale or in the pilot scale in this case, to manage the process. The first one was on the top left that you can see here. Here we have to control the formation of foam because we are not working with a pre-treatment, so the suspended solids and the organic compound are inside the stripper reactor, and so we have to manage the anti-foam. We have to use anti-foam chemicals. Anti-foam chemicals to avoid the formation of foam inside the empty part of the stripping reactor. And also we add a circulation pump that take the concentrate from the bottom and move on the top part to destroy the physically, how much is possible, the formation of foam. And the second problem that we solve inside our real plant, or in this case a testing plant, is the formation of aerosol. In fact, we have a great formation thanks due from the temperature, so evaporation of ammonia and steam, but also the movement based by the air bubbles inside, we have a formation of aerosol. So we have to create some equipments. In this case, are two demisters to try to stop the aerosol before to entering the scrubber, to don't have too much dilution of the solution inside the scrubber that can cause some problems from a technical or operational point of view, and also for the formation of the salts that we are going to do. And here you can see the demister that we created, implemented, and this was the stripper with the heating system that in this case was managed by electric resistance systems. So if I have to say some advantages of these technologies, first, that the air stripping doesn't need a pre-treatment because the solution is going directly in the stripper, and so we can almost treat all kind of wastewater, and with a high concentration of solid and hardness, and because it doesn't have the stripper, because it's a tank, problems for closing or scaling. And thanks to this, we are not to produce sludge from the treatment that can be really high advantages for the management point of view, and also cost maybe for the management of the sludge that we are going to produce. And potentially, thanks to the degradation of carbonates, the pH moves up alone inside thanks to the reaction inside the reactor. So the use of chemicals to basify the centrate are not strictly necessary. So the use of soda in this case was not so important, was not necessary at all for all the tests. But in the same time, the technologies has some disadvantages. The first one, and main one maybe, is the low efficiency instead of column stripping, because we can arrive around 80% and not to 100% that can be reached with the column stripping. And also, there's another problem that to have this kind of treatment, we need a high retention time inside the stripper. That was more than 10 hours. That means that to have a real scale plant, we need a large volume for the reactor or the stripping, and that means a lot of energy to heat the solution that we are going to from 50 to 65 degrees to have the reactions. And so we need a lot. We have a lot of dispersion, thermal dispersion, and in the same time, we have to heat the solution for a long time. Also, as I said before, a part that is quite important is the purge that is necessary, and this is going to create odors or emissions in atmospheres that have to be treated. And but also in the same time, the air that we purged, as I said before, we have to integrate with a fresh air that has the temperature, ambient environmental temperature. So this needs more energy again for thermal as thermal consumption to heat up the air to don't and in the same time the wastewater that we are heating and we are treating. And the last one is the formation, as I said, of foaming that has to be managed maybe with chemicals or physical system inside the plant. Now we are going to move again the voice to Omar to present the demonstration phases and the results. Thank you.
I'm back. So in the demonstration phase, we tested the two technologies into different wastewater treatment plants. The first one is Campo San Piero, managed by ETRA, and the second one is Fusina, managed by Veritas. We used two different centrates. In Campo San Piero, we use a centrate derived from organic waste and green waste for the anaerobic digestion of these two waste. And in Fusina, we use a centrate derived from the anaerobic digestion of sludge. It means we had four demonstration phases. In this table, you can see the numbers of the main parameters of the centrates we treated in these four cases. Demo 1 and Demo 3 used the same centrate, that is the one produced in Fusina. Of course, it changes during the time, but more or less it's the same. But I have to underline that in Demo 2 and in Demo 4, we use the same centrate, but in Demo 2, with aeration stripping, we were able to treat the centrate as is, with a very high load in terms of solids, ammonium, and alkalinity, without any problems. While in Demo 4, we had to, with the column stripping, that was already, as already said by David, is more sophisticated and more sensitive to solids and alkalinity. We had to dilute the centrate more than 20 times to be able to treat it. In general, well, I'm talking about the tests of yields versus the most important parameters that govern this process, that are temperature and pH. In general, we had the normal trends, expected trends against these two parameters. We noted that aeration stripping can reach lower yields in general than column stripping. As you can see, comparing the lines, the blue lines on the right with the blue lines on the left, and the green one with the green one on the left. And another thing, you can see that we have mainly linear regressions, linear curve, except for the relation between yield and pH in column stripping case, just because it doesn't happen in aeration stripping because of the range of yield we are considering. But in general, this curve is asymptotic towards a maximum. These results are as expected, and I think it's more interesting. Well, I can say note that with column stripping, we can reach almost 100% of removal of ammonia, while with AS we reach more or less 80%. But in the normal conditions of using of AS, we usually stay around 70%, because with aeration stripping, usually we use only the temperature to promote the stripping without using any chemical. And so at 60 degrees, we reach more or less 67–70% of yield. Some interesting things. Column stripping, as already said by Davide, it's very sensitive to alkalinity. In Fusina, the first demo, we had some troubles with the dosage of the chemicals, and so we had to use much sodium hydroxide instead of lime, and it influenced very much the removal of alkalinity, because with solid removal we have no problems, as you can see in the upper chart. But if you see the lower chart, you can see that in Fusina the alkalinity increased instead of decreased. The reason is why sodium hydroxide is not able to remove alkalinity. Lime can do it, sodium hydroxide can't do it. And more, sodium hydroxide adds its own alkalinity, and so the total alkalinity increased. In Campo San Piero, the Puracqua resolved the problem with a substitution of a pump, I think, and there we were able to use much more lime, and lime take off alkalinity. Another thing that you can see, I'm sorry, OCA 1, 2, and etc. are the operating conditions of the different tests. OCA 2, 5, and 8 are the condition at different temperatures, but always at pH 10. And you can see that this is the best condition to remove alkalinity. Probably because at 9 the dosage of lime is too low to have a good removal of the carbonates and bicarbonates, and to reach 11 pH 11 from 10, we had to add sodium hydroxide that adds its own alkalinity. And so reduce the yield in terms of removal of alkalinity. We had a consequence because in Fusina we had to stop the plant, open it, and do pickling to remove scaling. About aeration stripping is of particular interest, the relation between yield and air purge, already explained by Paolo. The reason of this purge is that inside, I repeat this idea, this issue. Inside of the wastewater, you have free CO2, that is a gas that is dragged by the air stream that crossed the wastewater. But you have also in our centrate, in the centrate we produce, you have also a lot of carbonates and bicarbonates. These ions are decomposed particularly by the temperature. And the decomposition of these ions produce CO2. You have to take off this CO2 to avoid to permit the pH to rise further, and just because in this way you can release the ammonia that is mainly bound with carbonate and bicarbonate. But this means that inside the airstream you accumulate CO2. This produced two consequences. The first is an overpressure, and you have to purge a part of the airstream to restore the correct pressure. But it's not enough, because anyways the concentration of CO2 in the air tends to increase, and if it increases too much, the decomposition of carbonate and bicarbonate stops, and we have to avoid it to have better yields. So we have to purge more air and substitute it with fresh air. The tests we did to see the relation between yield and air purge showed us that you increase the yield until a certain percentage, that in this case is 40%, more or less. But after this percentage, the further purge is unusual. It's of course, because at this percentage, the concentration of CO2 inside the airstream is very low, and it's negligible and doesn't influence the decomposition of carbonate and bicarbonate. Two notes. The first is that purge is not an absolute number that is valid always, but it depends on the concentration of alkalinity inside the centrate. The higher is this concentration, the higher must be the percentage of purge. The second is very clear from this chart. That is the problem that the fresh air cool the air and cool the water inside the centrate, inside the stripping reactor, and you need much more energy to heat it. And as you can see, this trend, the consume of energy is much more when the air is when the air temperature is low. Please don't pay too much attention to the kilowatt hours, because we at the pilot scale it's impossible to do many optimizations, such like heat recovery, for example. But the trends remain very significant. Another interesting thing about aeration stripping is that you need very long retention time. It's a problem for the energy consumption. And we tested it. We tested the yield, the trend of yield versus retention times, and we saw that it's asymptotic towards the maximum. And so you have to choose the right retention time that can save energy, but make it able to reach the desired yields. About the product, ammonium sulfate we produced. We checked it, we controlled it with 5 analyses and with more than almost 200 parameters. And we saw that the first problem is that it's very dilute. You have to think that at the maximum we can reach with stripping technologies 30–35% of ammonium sulfate inside the solution, not more. And it means that if you have to transport it toward a user, you have to transport 65–70% of water. It's not very economic, and it's an impact also in terms of environment. And more, we saw that it's very important to control the production of condensate and droplets inside that circulate inside the airstream, because it produces further dilution of ammonium sulfate. Finally, a brief comparison between the two technologies. Aeration stripping is very good technology when you have a centrate very loaded with very high concentrations of solids, of salinity, because it's very robust. It's very simple, and it's an advantage both in terms of construction and management, but also very robust and versatile. Another thing is that it doesn't need a pretreatment, and so you usually don't need to use any chemical, and you don't produce any sludge. Of course, as already said, the problem is that you need long retention times, and so you need much space and much and more heat than column stripping, and you need purge, and so you need more heat too. With this process, there is a problem of producing foam producing, and then you have to expect lower yields than column stripping. Column stripping is a very effectiveness plant technology. You can reach almost 100% of removal of ammonia. You don't need longer retention times, and it means that you have to heat the water only for time needed to cross the column, and it's a strong advantage in terms of energy consumption. But as we saw, it needs a pretreatment because the column is very sensitive to alkalinity, to scaling and cloggings in general. And this means that you need to use systematically different reagents, different chemicals, producing also sludge. And more, this is a sophisticated technology. Sophisticated, it means that it is more expensive in the moment of the design and during the construction, and it's more also in terms of management. More things to plan, and more expertise needed from the people that manage the plant. What else? This table resumes what I have said. If you have some question, we are here. I hope that what I have said is clear. And please fill in the evaluation form, because we have to relate about it.
I send you also the link in the chat, so please, I'm asking, and it's also compulsory to do it for the project of B-WaterSmart. So, and if you have any kind of question, please turn on your microphone and let us know. Yeah.
I stop the share of my video. Okay, if nothing, if you have nothing to declare, I wish you a good day. Thank you, Fatima. I wish you a good day, and I invite you again to fill in the form of the link. Thank you very much. Do you have something to say? Okay. Thank you very much. Have a nice day. Goodbye.